The cholesterol myth. Misunderstood molecules and human survival. Cholesterol might be one of the most misunderstood molecules in the human body. Most people have heard that high cholesterol is dangerous, that LDL is the bad cholesterol, HDL is the good cholesterol, and that cholesterol can clog your arteries, leading to heart attacks and strokes. But at the same time, cholesterol is absolutely essential for human survival. Your liver manufactures cholesterol on purpose because you cannot survive without it. So if cholesterol is so important, why is it also associated with cardiovascular disease? Why do some people with elevated cholesterol develop arterial plaques while others don't? I think due to this confusion and how cholesterol can silently impact your long-term health, this is going to be one of our more important videos. We'll cover what cholesterol actually is, the difference between HDL, LDL, and other markers like ApoB and Lp(a). We'll discuss how eating cholesterol and fats influences your levels, how your body absorbs and transports cholesterol, when it becomes a problem forming arterial plaques, and what you can do to reduce cardiovascular risk. Let's jump in. Chemical structure: hydrophobic sterols versus cellular fluidity. Before understanding how cholesterol contributes to atherosclerosis, we need to understand what cholesterol actually is. Cholesterol is not inherently bad. It is absolutely essential for survival. Chemically, cholesterol is a lipid molecule known as a sterol. Fats are the most common lipids, but sterols are just another type. One major characteristic of lipids is that they are hydrophobic, hydro meaning water, phobic meaning fear, so lipids do not mix well with water. That detail becomes extremely important later. One of cholesterol's biggest roles is helping build and maintain cell membranes. Every cell is surrounded by a membrane, primarily made of phospholipids, with cholesterol embedded within, regulating membrane fluidity and providing structural stability. Cholesterol is also used to synthesize steroid hormones: testosterone, estrogen, cortisol, progesterone, and aldosterone. Your body also uses cholesterol to produce bile salts, components of bile produced by the liver. The gallbladder, this little bag-like organ underneath the liver, stores bile, which is extremely important for digesting dietary fats. Cholesterol is also involved in vitamin D synthesis, and your nervous system uses it to build myelin sheaths around neurons, fatty insulation surrounding axons that helps electrical impulses travel rapidly. So, cholesterol is not a foreign invader. It's a molecule your body intentionally manufactures for multiple physiological functions. This brings up another point of confusion. Many think cholesterol only comes from food, but your liver constantly synthesizes it. Your body is so dependent on cholesterol that even with very little dietary intake, it would continue manufacturing it. Diet is not irrelevant. Nutrition absolutely influences cholesterol levels and cardiovascular risk, but cholesterol is not simply something you put into the body. Your body actively creates it to survive. Physiological functions: steroid hormone, bile salts, and myelin insulation. Now we run into a problem. Cholesterol is hydrophobic, but our blood is mostly water. Your body needs a specialized transport system, eventually leading us to HDL and LDL particles. But let's first figure out how the body transports cholesterol, both synthesized and dietary. Start with dietary cholesterol, found in eggs, meat, dairy, and other animal products. Once swallowed, it travels down the esophagus. Here's one removed from a body. To orient you, the larynx would be right here on me. The trachea is below it, and behind the trachea is the esophagus. Cholesterol enters the stomach, where, interestingly, it's not heavily digested since it's already a small lipid molecule. It doesn't need breakdown like proteins or carbohydrates. It mostly survives intact and moves into the small intestine. This is where things get interesting. The small intestine is a watery environment, and cholesterol is hydrophobic. Your body uses bile to help. Bile from the liver and gallbladder is released into the small intestine and contains bile salts. amphipathic molecules where one side interacts with water, hydrophilic, and the other with lipids, hydrophobic. This lets bile salts act like biological detergents, surrounding dietary lipids and bundling them into tiny transport clusters called micelles. Micelles contain cholesterol, fatty acids, monoglycerides, phospholipids, and fat-soluble vitamins. These hydrophobic molecules, which would otherwise struggle in the watery intestine, are shuttled within the micelle toward absorptive cells called enterocytes. Entero meaning intestine, cyte meaning cell. The micelle itself isn't absorbed. Instead, it brings lipids close to the brush border, where cholesterol is moved into the cell by membrane transporters. Once inside, cholesterol gets repackaged with triglycerides and other lipids into a massive lipoprotein called a chylomicron. These are so loaded with lipids, they cannot enter normal blood capillaries. How chylomicrons bypass the bloodstream via lacteals. Normally, nutrients like amino acids and glucose move from enterocytes into the bloodstream and directly to the liver. But chylomicrons are too large, so they enter specialized lymphatic capillaries called lacteals. Cholesterol and other lipids bypass the bloodstream and liver initially, entering the lymphatic system instead. Chylomicrons move from lacteals into larger lymphatic vessels, then into the thoracic lymphatic duct, the largest lymphatic vessel in the body, which empties them into a vein under your left clavicle, technically at the junction of the left subclavian and left jugular veins. Now the chylomicron is finally in the bloodstream. Once in circulation, chylomicrons deliver triglycerides to tissues throughout the body. As they circulate through capillary beds in skeletal muscle, cardiac muscle, and adipose tissue, they encounter lipoprotein lipase, an enzyme that breaks triglycerides into free fatty acids for energy or storage. As triglycerides are removed, chylomicrons become smaller, denser, and proportionally richer in cholesterol, transforming into chylomicron remnants that travel to the liver for processing. To review, large chylomicrons enter the bloodstream containing triglycerides, cholesterol, and other lipids. Tissues pull out triglycerides for energy, making the chylomicron smaller until mostly cholesterol remains. This is the chylomicron remnant, which reaches the liver. Remnant metamorphosis. How lipoprotein lipase extracts triglycerides. One of today's main points is how cholesterol carriers like LDL and HDL relate to long-term cardiovascular health. Cardiovascular disease can develop silently over years or decades before symptoms appear, making biomarkers related to cholesterol, inflammation, and metabolic health extremely important. This is where today's sponsor comes in, Rhythm. It's an at-home blood testing service monitoring biomarkers for cholesterol, cardiovascular health, inflammation, metabolic health, and hormones. Many people only get blood work once a year, but physiology is dynamic. Diet, exercise, body composition, sleep, medications, and metabolic health all influence biomarkers over time. The process is simple. Peel, stick, and click the device onto your upper arm, completely painless. Within a minute, the collection tube fills with blood. They analyze LDL, HDL, triglycerides, ApoB, inflammation markers, and more. Remove the tube, snap the cap on, mix it around, and they'll pick it up from your house. This lets you follow trends over time because cardiovascular health is about cumulative effects over long periods, not single decisions. Go to rhythm.help/HA for free shipping on your first month. Link in the description below. Now let's get back to the video. Hepatic Command Center, direct bile secretion, and cholesterol gallstones. Once chylomicron remnants reach the liver, it unpacks and processes their lipid contents. The liver is the central command center of cholesterol metabolism. It synthesizes, recycles, and packages cholesterol. It converts cholesterol into bile salts, secreted into bile for fat digestion. And it can also directly secrete cholesterol into bile. These are two different things: converting cholesterol into bile salts versus direct secretion. Direct secretion helps eliminate excess cholesterol through the digestive tract. Fun FYI, bile components contribute to normal stool color. I remember a patient early in my urgent care career who came in because she had white-colored poop, an indicator of liver, gallbladder, or bile duct issues. Another FYI, if bile becomes too saturated with cholesterol, it can precipitate out and form cholesterol gallstones, the most common type. The liver also needs to transport lipids back into the bloodstream for delivery to tissues, leading us to VLDL, IDL, LDL, and HDL particles. You might wonder why the liver repackages lipids and sends them back out. Cells constantly need triglycerides, cholesterol, and fatty acids, not just after meals. Plus, you may not have eaten a lipid-rich meal, so the liver must repackage and send cholesterol out. The first particle is VLDL, very low-density lipoprotein. Like chylomicrons, VLDL contains cholesterol, but is more heavily loaded with triglycerides. Once in circulation, lipoprotein lipase removes triglycerides for tissue use. VLDL becomes smaller, denser, and richer in cholesterol, transforming into IDL, intermediate density lipoproteins. As more triglycerides are removed, they become even smaller, forming LDL, low-density lipoproteins. Lipoprotein densities, the real difference between VLDL, IDL, and LDL. This brings us to one of the most misunderstood topics in cardiovascular physiology. LDL is often called bad cholesterol, but LDL is not cholesterol itself. It's a lipoprotein particle that transports cholesterol. Calling it an LDL particle rather than LDL cholesterol is more accurate. LDL particles serve important functions, delivering cholesterol to tissues for cell membranes, hormone synthesis, and other functions. They were not designed to cause cardiovascular disease. They're part of a normal transport system. HDL, high-density lipoproteins, are the other major particle. The density names reflect different lipid-to-protein proportions. LDL has more lipids relative to proteins, making it low density. HDL has more proteins relative to lipids, making it high density. While LDL transports cholesterol outward to tissues, HDL transports cholesterol back toward the liver, called reverse cholesterol transport. HDL may also have antioxidant and anti-inflammatory functions, which is why HDL is called good and LDL bad. But the real physiology is much more nuanced. Atherogenic retention. Why ApoB particles bind to proteoglycans. LDL is called bad because it's atherogenic. It can contribute to atherosclerosis, plaque formation within arteries that narrows them and can lead to heart attacks and strokes. LDL particles do this because under certain conditions, they can enter and be retained in the arterial wall. This triggers oxidation, inflammation, foam cell formation, and ultimately plaque development. More retained atherogenic particles mean larger plaques. But LDL isn't the only atherogenic particle. VLDL, IDL, remnant particles, and lipoprotein A, Lp(a), are also atherogenic. What they share in common? A protein called apolipoprotein B, ApoB. LDL, VLDL, IDL, remnants, and Lp(a) all carry ApoB on their surface. HDL does not. ApoB binds to proteoglycans in the arterial wall, causing particles to get stuck and contribute to atherosclerosis. These particles become atherogenic under certain conditions. Plaque formation is usually multifactorial, multiple conditions and risk factors over decades. Simplified, two main contributors drive plaque formation: abnormally high levels of ApoB-containing particles, plus endothelial dysfunction and damage. The endothelium is the inside lining of arteries. Healthy endothelium regulates vascular tone, blood flow, inflammation, and substance exchange. Certain conditions damage this lining over time. Hypertension, increased mechanical stress. Smoking, oxidative stress and inflammatory chemicals. Diabetes/insulin resistance, chronic inflammation, metabolic dysfunction, and glucose damage. Obesity, sedentary lifestyle, poor sleep, chronic stress, and poor diet patterns. Inflammatory and metabolic conditions increasing cardiovascular risk. This is cumulative. The number of circulating atherogenic particles, how long arteries are exposed to them over years and decades, plus endothelial dysfunction, inflammation, and metabolic disease all interact. At normal levels, these particles transport lipids without causing problems. Elevated levels increase retention risk. Adding endothelial damage makes particles even more likely to get stuck. Endothelial dysfunction, mechanical strain, smoking, and insulin resistance. Genetics play a major role. Some inherit conditions causing extremely elevated LDL or abnormal Lp(a), increasing cardiovascular risk even in healthy individuals. But controllable lifestyle factors can help lower atherogenic particles. Medical interventions. How statins modify hepatic receptor activity. We can influence both sides, reduce circulating atherogenic particles, and reduce endothelial damage. Medications can help. Statins are the most well-known, working by reducing liver cholesterol synthesis and increasing LDL receptor activity on liver cells, allowing the liver to pull more LDL from the bloodstream. For some individuals, these dramatically reduce levels. Lifestyle protocols. Saturated fats, soluble fiber, and vascular health. Lifestyle modifications also have major effects, starting with diet. Dietary cholesterol itself often has a smaller effect on blood levels than many think. Diets very high in saturated fats have greater influence on increasing LDL particle levels, though genetics affect how dramatically a person responds. Saturated fats influence how the liver regulates cholesterol metabolism and LDL receptor activity, reducing the liver's ability to remove LDL from the bloodstream. Diets high in refined carbohydrates and excess calories contribute to obesity, insulin resistance, elevated blood glucose, elevated triglycerides, and increased VLDL production, which eventually become LDL. Diets rich in fiber help reduce cholesterol absorption and increase elimination through the digestive tract. Exercise improves insulin sensitivity, metabolic health, blood pressure, body composition, endothelial function, and cardiovascular health. It may also improve triglycerides and lower atherogenic particles. Remember, plaque formation isn't just about atherogenic particles, it's also about endothelial health. Anything contributing to chronic inflammation, oxidative stress, or endothelial damage increases risk. Smoking cessation is critical. Managing blood pressure reduces mechanical strain on the endothelium. Improving sleep, reducing chronic stress, maintaining healthy body composition, and improving metabolic health all reduce vascular stress over time. This isn't about one perfect decision. Cardiovascular disease develops cumulatively and silently over decades. Small improvements consistently maintained meaningfully reduce risk. Stay on top of annual physicals, because the only way to know if you have elevated atherogenic particles is a lipid panel: triglycerides, LDL, HDL, and total cholesterol, with some panels estimating VLDL. Clinicians may add ApoB or Lp(a) based on results and risk factors. The biggest takeaway? Cholesterol itself is not inherently bad. Your body requires it for cell membranes, hormone synthesis, bile production, vitamin D synthesis, and nervous system function. The real issue is excessive exposure to atherogenic particles combined with endothelial dysfunction, inflammation, and plaque formation over years and decades. The goal isn't to eliminate cholesterol. It's to reduce excessive atherogenic particle exposure while protecting arterial health.